Pluto, the enigmatic dwarf planet residing at the outer reaches of our solar system, is once again captivating the astronomical community with an unexpected development. Recent reports suggest a possible future encounter between Pluto and Neptune, raising concerns among both scientists and space enthusiasts. Renowned experts, including Neil deGrasse Tyson and Michio Kaku, have voiced their alarms about the potential consequences of such a celestial clash. But how did Pluto, once demoted from its planetary status, end up on a trajectory that might lead to a cosmic collision with its distant neighbor? And what would such an event mean for us on Earth? Once considered the ninth planet of our solar system, Pluto was reclassified as a dwarf planet due to its unique characteristics and irregular orbit. Despite this change, Pluto has never ceased to intrigue astronomers. One reason for the current excitement is the recent prediction of a possible dangerous proximity between Pluto's path and Neptune's orbit, a scenario that has prompted speculation about a catastrophic collision. If these two celestial bodies were to collide, the consequences could be far-reaching, potentially posing risks to other planets, including Earth. Pluto's journey around the Sun is unlike any other planetary orbit in our solar system. Its orbit spans a staggering 248 Earth years, meaning that since its discovery in 1930, Pluto has yet to complete even one full revolution around the Sun. What makes Pluto's orbit even more peculiar is its highly elliptical shape, as opposed to the nearly circular orbits of the major planets. Additionally, its path is inclined at a steep 17 degrees angle to the ecliptic plane, which sets it apart from its planetary peers. One of the most fascinating aspects of Pluto's orbit is its periodic intersection with Neptune's path. For approximately 20 years during each of its orbits, Pluto ventures closer to the Sun than Neptune, defying the traditional understanding of planetary distances. Given this crossing, a natural question arises. Why haven't Pluto and Neptune collided? The answer lies in the delicate gravitational dance between these celestial bodies, governed by the complex mechanics of space. Astronomers have long studied the dynamics of Pluto's orbit, especially its peculiar relationship with Neptune. While Pluto crosses Neptune's orbit, a collision has been avoided due to what is known as the three-body problem in celestial mechanics. This problem involves understanding the gravitational interactions between three celestial bodies, in this case, Pluto, Neptune, and the Sun. The intricate gravitational influences and the specific timing of Pluto's approach to Neptune prevent the two planets from ever meeting in a direct collision. Terms like libration, latitude libration, and Chi oscillation are critical in understanding the stability of Pluto's orbit. For example, Pluto's azimuth libration ensures that when it crosses Neptune's orbit, it is positioned at least 90 degrees away from Neptune, effectively avoiding any risk of collision. Latitude libration adds another layer of protection by positioning Pluto significantly above or below Neptune's orbital plane during close approaches. This gravitational choreography keeps the dwarf planet and its giant neighbor from clashing despite their overlapping orbits. However, recent numerical simulations have suggested that while Pluto's orbit has remained stable over the course of billions of years, its path is technically chaotic. Even minor deviations in its initial conditions, such as a slight shift in its velocity or position, could lead to significant changes in its long-term trajectory. This introduces an element of unpredictability, causing some scientists to raise concerns about the potential for future instability. In the late 1980s, advanced computer simulations helped to further unravel the mysteries of Pluto's orbit, showing that while the dwarf planet's path is chaotic, it remains stable over long periods. The simulations revealed that the gravitational influence of Neptune, along with Jupiter and Saturn, plays a crucial role in keeping Pluto's orbit in check. Neptune completes 3 orbits around the Sun for every 2 orbits completed by Pluto, a phenomenon known as orbital resonance, which significantly contributes to the stability of both planets. Despite this stability, the simulations also indicated that Pluto's orbit is not immune to change. Over millions of years, small alterations in the gravitational forces exerted by the larger planets could disrupt its path. Astrophysicists like Neil deGrasse Tyson and Michio Kaku have pointed to this unpredictability as a potential threat, suggesting that a collision between Pluto and Neptune, while unlikely in the immediate future, could occur over a longer timescale. Tyson, who famously advocated for Pluto's reclassification as a dwarf planet, views these findings as an opportunity to reassess our understanding of celestial mechanics. He emphasizes that while the reclassification of Pluto was seen by many as a demotion, it was a necessary adjustment to reflect our evolving knowledge of the solar system. The unusual characteristics of Pluto's orbit, Tyson argues, remind us that there is still much to learn about the complex gravitational interactions that govern planetary movements. Both Tyson and Kaku have raised concerns about the potential for a collision between Pluto and Neptune, which they argue could disrupt the balance of our solar system. Such an event would unleash massive amounts of energy, likely shattering Pluto and scattering debris across space. While the direct impact on Earth would be minimal due to our distance from these outer planets, the shockwaves could have far-reaching implications for other celestial bodies, potentially altering their orbits and introducing new hazards. Michio Kaku, known for his work in theoretical physics, offers a unique perspective on the scenario. He sees the study of Pluto's orbit as critical not only for understanding celestial mechanics, but also for advancing our knowledge of space exploration. According to Kaku, insights gained from studying Pluto's gravitational interactions could help future missions navigate the outer reaches of the solar system. Moreover, Kaku connects the dynamics of Pluto's orbit to deeper theoretical concepts, such as string theory, which seeks to explain the fundamental forces and particles of the universe. Kaku suggests that a collision between Pluto and Neptune would create extreme conditions of energy and gravity, providing a rare opportunity to observe and test the behavior of fundamental particles under such conditions. The gravitational waves produced by such a collision could offer valuable data for testing predictions of string theory related to gravity and spacetime. While the immediate risks of a Pluto-Neptune collision are low, the event could yield profound scientific insights, contributing to our broader understanding of the universe's underlying principles. 0021. As we continue to explore the depths of space, Pluto's chaotic yet stable orbit serves as a reminder of the unpredictability inherent in the cosmos. Understanding the forces that govern celestial mechanics is essential not only for predicting potential hazards, but also for gaining a deeper appreciation of the intricate and dynamic nature of the universe. While a collision between Pluto and Neptune may remain a distant possibility, the study of these celestial bodies continues to captivate and challenge our understanding of the cosmic ballet that unfolds in the far reaches of our solar system. As the cosmic clock ticks, one might wonder if Pluto, the enigmatic dwarf planet, is inching toward an apocalyptic rendezvous with Neptune. What if the unthinkable occurs? Recent studies have reignited concerns about a potential collision between these distant worlds, stirring unease among astronomers and stoking the fires of public curiosity. This celestial clash, if it ever happens, would not only captivate our imagination but also present profound scientific implications. Imagine a collision so intense that it could disrupt the delicate balance of our solar system, sending ripples through the very fabric of space. What could such a cosmic event teach us about the universe's hidden mechanics, and how might it affect our understanding of celestial dynamics? To grasp the gravity of this cosmic possibility, it's essential to delve deeper into the mysteries of Pluto's orbit. Despite its reclassification as a dwarf planet, Pluto's journey remains one of the most intriguing in our solar system. With an orbit that takes 248 years to complete and a trajectory so steeply inclined that it crosses Neptune's path, Pluto's movements challenge our understanding of celestial mechanics. The critical question is, why does this collision seem so improbable despite their overlapping orbits? The answer lies in a delicate gravitational dance involving Neptune, Pluto, and the other giants of our solar system. As they move through space, these planets influence each other's paths in ways that prevent a direct clash. Their gravitational interactions create a cosmic choreography, ensuring that Pluto and Neptune avoid a catastrophic encounter even as their orbits intersect. Yet, even with these protective mechanisms, the universe remains a realm of constant change and potential chaos. The possibility of future disruptions, whether from rogue planets wandering through the void or from unforeseen cosmic events, reminds us of the universe's unpredictable nature. Scientists continue to scrutinize these celestial interactions, using advanced simulations to predict and prepare for potential scenarios. As we look to the stars, the story of Pluto's orbit serves as a vivid illustration of both the stability and chaos that define our solar system. This ongoing exploration not only deepens our understanding of planetary dynamics, but also fuels our quest to uncover the secrets of the cosmos. Who knows what new revelations await us as we continue to unravel the mysteries of space? The cosmic drama is far from over, and every discovery adds a new chapter to our understanding of the universe.